All right, if you recall in the last segment, we began to develop an array of expressions to get thermodynamic quantities from the partition functions, right? Specifically, we worked through equations that got us to expressions for entropy, and then for the Gibbs, not the Gibbs, the Helmholtz free energy, which I then used towards the end of that video to get an expression for pressure. And we saw that matched the expected result from the ideal gas law. Right. This piece, we're going to work through some additional thermodynamic functions, in particular two that are very commonly used in chemistry, namely enthalpy and the Gibbs energy. So starting with enthalpy, we have just the definition statement for what we mean when we talk about enthalpy is always that we can say it's the internal energy U, which is that piece there, plus PV, right? That's the definition of enthalpy, which was originally put together in order to generate a function which is equal to the heat at constant pressure, and that's the role that we usually use enthalpy in, right? We have from last time and from earlier an expression for the internal energy, right? And in terms of our molecular partition function, that is this result here. We showed at the end of the previous video that PV is equal to NKT, at least in the limiting case that the particles are not interacting with one another, not sticking together at all. Right? But if we take that and go with it, then we would get this for our enthalpy, right? Where this piece here, this is my U, and this piece here is PV. Right, so that's U plus PV. It matches what we expect and need for it to be the enthalpy. Okay, so that gets us a route to enthalpy. Once we have enthalpy, we're equipped to go and get the Gibbs free energy, which is usually the favorite of the various free energies among chemists, because it is the one that matches conditions that we most often encounter. Right? And if I go to work on the Gibbs energy, again, the defining statement for that is that G is equal to H minus TS. Right? That's the statement that tells us what the Gibbs energy actually is. We have expressions now for entropy from last time and for enthalpy from just now. And so we can put both of those into our equation, right? If we do that, we have the reminder of the entropy expression here, right? Which we can write this way. And I know that last time we did a little bit of manipulation to make that into a simpler form. I'm going to keep it that way right now because I'm going to be able to disappear a few terms when I combine these things. Right? The enthalpy expression that we just assembled is below that. Right? If I put those in here, what I've got is this piece up here. This is H. Right? That's H. This piece down here the T is out front and everything inside of those square brackets is S, right? So I should have, I drew that a little bit further than I meant to. It should be more like there because the square brackets is S, right? So that is H minus TS. If you look through that, and we have to be a little bit careful because I've got this T out here multiplying things, right? So this term here becomes NKT squared times the derivative of natural log of Q. That's got the minus sign also out here, so that means that this term will cancel with that one, right? I've got an NKT here, and here I've got an NK inside the brackets being multiplied by minus T, so that means I have plus NKT up here and minus NKT down there, so those terms will also cancel. And you can see why I kept that form for the entropy now to make it relatively clear that we could do that. That means the only piece that survives is this part right here, right? And so when I grab that and put it over here, this thing gives me an expression for G, the Gibbs free energy, based on the temperature and the molecular partition function together with the number of molecules, right? N is the number of molecules. We could easily take that and make that into a molar value, and we'll do that shortly as we attempt to think about what we would have to do if we wanted to actually use these expressions to calculate delta H or delta G, say, for a chemical reaction. Right? We have all the tools we need to do that right now. Having said that, I will admit that the actual calculation is rather daunting. Right? We won't undertake that in this particular chunk of video, but sometime soon there'll be a video in which I spend a ridiculously long time doing a calculation to get an equilibrium constant from a variety of these thermodynamic functions. And so when I say this means we can calculate these things, it doesn't necessarily mean that we can do it easily. I left in a question again, because I'm kind of thinking that's a good and useful thing to do for you. And so we'll take a look at this one again. As usual, when these are up here, if you want to take some time and think about things on your own, you can pause the video and contemplate for as long as you want. What have I got here? I've got a system that's got, I drew it with 3 energy levels, right? And my 3 energy levels are equally spaced because the bottom energy I labeled as 0, then epsilon and 2 epsilon. So when I say equally spaced, I mean the gap between n equals 1 and n equals 2, and n equals 2 and n equals 3, those are the same size gaps. Right? And the question is the ratio of the probabilities, P3 over P2, how would that compare with the ratio of P2 over P1, right? And so take a moment and think about that. This is a question that, again, often causes some substantial discussion and debate in a room full of students. And so I encourage you to just give it a moment's thought and decide what you're thinking. I will, however, just proceed. And of course, there's only 3 possible choices for this, right? We're comparing two quantities, either one or the other is greater, or else they are equal, right? To address this, you should think about what that ratio depends on, right? Each probability depends on e to the minus. The probability that goes, it's proportional to e to the minus the energy over kt, let's say, right? Where that's just the energy for whichever state I'm talking about, right? If I take that ratio, that means that the ratio that'll get me wanting to be, that'll come from e to the minus what'll be delta E over kt, where delta E is the energy gap between the two states, right? In this case, because of the way we set up the states, our energy gaps between 2 and 3 and between 1 and 2, those are the same, right? That means that delta E for the 2 combinations we're comparing is the same, and that means that these two probability ratios should actually be equal, right? If I were to look at, I mean, the ratio of 2 over 1 is definitely going to be bigger than the ratio of 3 over 1, because then my energy gaps are not the same anymore, right? But if I'm comparing equally spaced levels, as long as their delta E's are the same, then that ratio is always going to come out to be the same number. And if that doesn't seem to make sense to you, I encourage you to take a look at the equations and try to convince yourself that that is how it should work out. It's a little bit non-intuitive in some cases to a lot of people, perhaps myself included on first confrontation of this. And so it's a good thing to kind of wrestle with a bit if you need to. All right, moving ahead with the equations we've gotten, what I want to do is just set up at least the idea of how we could go about calculating the various quantities for an actual chemical reaction. All right, and so suppose that I wanted to work my way towards getting something like delta G for the reaction on the bottom of the screen. The reaction on the bottom of the screen, if you think back to thermodynamics, even in Gen Chem, that is what is known as the formation reaction for liquid water, right? Because it makes 1 mole of liquid water, or gas phase water, I'm sorry, I wrote gas on there. So it makes 1 mole of steam from 1 mole of hydrogen gas and 1/2 mole of oxygen gas, where those 2 things on the left are both elements in their standard state, right? So when I wrote this here with the subscript F on there, that's just the notation that says it's the formation reaction, right? So that is the standard molar free energy change for this particular thing. So suppose we wanted to calculate that, and suppose that instead of doing calorimetry measurements or anything like that, actually trying to react the hydrogen and oxygen, we wanted to do this by doing statistical methods, okay? We might actually want to do that because in this case, the reaction itself tends to be explosive, right? So measuring the heat flow associated with that is not a simple process. If I wanted to do that, I would be able to say that I can write delta G for the reaction. It's always what the G's for the products minus the G's for the reactants, right? That's what it means to be delta G, after all, and each one is multiplied by the coefficient from the equation, right? So this just says the water is the product, here's the hydrogen, here's the oxygen. Those are now the standard molar free energies for those things, right? That are shown in my equation there, right? And so we know this expression, right? We have the equation for G that says it's minus nkt natural log of Q, the molecular partition function, over N. If I want to make that into a molar quantity, since we usually do thermodynamics that way, right? And so if we want to go to a mole, that says that N becomes Avogadro's number, right? Because the number of particles in a mole is Avogadro's number. When I do that, Nk here, that becomes R, right? And N on the bottom here, that one just becomes N sub A for Avogadro's number, right? So that's now a molar value for the free energy, right? Suppose I wanted to actually use that idea and take that to calculate my delta G for this reaction. What I would need is I would need to find those molar free energies, the G sub M values for the steam and the hydrogen gas and the oxygen gas, right? Once I got to those, I could insert them into the equation up above and calculate my delta G, right? So if I wanted to do that, what I would need is I would need values for those partition functions, the molecular partition function for each of those things. That means I would need to look up a variety of information, right? Hydrogen and oxygen are nice diatomic molecules, the sorts of things we've been working with, right? So for those, we would have to know something like either those theta parameters, the temperature parameters for vibration and rotation, or alternatively, we could know something like the vibrational frequency, and if we knew the bond length, I guess we could use that to get the rotational constant, right? Because we could get that from knowing the masses, we could find the moment of inertia. So that would be a set of data that would get us the things we needed to do the H2 and O2. For the water, we'd have a little bit more to do because we'd have to do all those things, right? And finding the rotational number, if I had to calculate it from the moment of inertia, I have to do a little bit more work for the moment of inertia because now it's not just a linear molecule, right? Because it's not a linear molecule, it also would have now it'll have 3 rotational degrees of freedom, and it would also have multiple vibrational frequencies, right? Because now that I'm triatomic, I have more total degrees of freedom, right? And so I'd have more vibrational frequencies or vibrational theta parameters to look up. But presumably I could get all that information. I haven't looked to check, but I suspect that the things we would need for those simple molecules probably appear in that table that's in your textbook if we really wanted to do that full calculation, okay? I'm not going to do the whole calculation as it turns out. Because that's not really what I'm after here. But if I did that, what would I have to do? These would be the things that I've got there, right? And so if I took that, all those different bits of information, I could work my way towards getting the total molecular partition function, right? So once I got my translational, we need a molar volume too to get the translational partition function, right? So I'd probably do something like assume they're ideal gases and make their molar volume that 22.4 liter number that some of you might remember from gas law problems, right? If I did all that, once I got the total partition function, which I would get by multiplying the translational piece times the appropriate number of rotational pieces and so on, then I would say something like delta G for the whole thing is just going to be equal to minus RT ln of Q over N sub A for the water. There's going to be an RT on all of them, I guess, so maybe I'll do it this way. Then I would have minus ln of Q over N sub A, and obviously N sub A is the same inside these things, but I'm going to keep writing them that way, I guess, since I started that way. Right, so most of the work in actually doing the calculation this way would come in the part where I had to assemble those partition functions, right? Even that, if I could look up those theta parameters, then it's not that terrible to calculate those. In the case of the water in particular, I have to be careful and make sure that I count up the number of vibrational modes correctly and get them all accounted for. But when we looked up the constants, it would generally tell us things like what the degeneracy of any of the vibrations was and things like that. And so it does show that we could, in fact, go ahead and calculate things in that way, right? My partition functions are going to be large numbers because the translational part is going to be big, but then I'm dividing them by Avogadro's number in there, which of course is also a large number. And so in the end, I'll have numbers that are workable. And we could actually do that calculation, although I did not write out notes for the actual values of them, and I don't want to spend that much time calculating them out right now. So we won't venture into that. All right, so that's an example of how we would go about doing this sort of thing. We'll kind of tie up this part. I want to take the idea, since we mentioned a polyatomic molecule there in the water, and go back to that to make one more look at heat capacities. I know that the heat capacity has been the one reliable thing that comes in periodically throughout this set of videos, and so I think it's good to touch base with that again, right? Our general expression for the heat capacity is one that's written there, right? And again, it's got these derivatives of the partition function in there, right? And we know how to find the partition functions for things. If we work with polyatomic molecules instead of diatomics, the only thing that changes is that we have to manage to account for the right number of rotations and vibrational degrees of freedom, right? In order to illustrate that, I'm going to think about a particular pair of molecules, okay? I'm going to compare the heat capacities for helium versus for ammonia, okay? So helium is very simple, right? It's a monatomic gas. It's the simplest possible case, so it has no rotation or vibrational parts to it, right? And so it has no possible contribution from anything except translation. The translational part, if we're doing this at room temperature, like it says, translational motion is pretty much always in the high temperature limit, which means we should expect that to be 3/2 R. Sure enough, for helium, if you measure the heat capacity anywhere near room temperature, you get a value that pretty much just is 3/2 R. The ammonia should also be same contribution from translation here for this one. For rotation, I can't rotate the helium because it has no moment of inertia, it's just a point. I can't vibrate it, and I do not expect a contribution from the electronic states because there's no real chance that near room temperature I'm going to promote an electron from the helium 1s orbital up to, say, the 2s, which would be the next one available, okay? If I get to rotations, my translations here, I always have 3 translations, right, for anything. That's just like XYZ degrees of freedom, okay? For rotations, ammonia is a nonlinear molecule, right? We've done diatomics mostly, and then we say, well, there's 2 rotations. For ammonia, there's actually going to be 3, because I'll have 3 different axes I can rotate that about, right? So I will have 3 rotations here. Okay, and when I have 3 rotations there, that means that my rotational contribution to the heat capacity, when all of those are in their high temperature limits, this will go to be 3/2 R instead of, we've often done R, right? The diatomics, we've been saying R, and that's just because there's only 2 rotations then, right? We're still doing 1/2 R for each of these degrees of freedom that is safely in its high temperature limit, okay? If I want to get to the vibrations, I have to think about how many vibrations there are first. Okay, if you remember back to when we talked about spectra a little bit, the total degrees of freedom for a nonlinear molecule, since ammonia is nonlinear, this is 3n. 3n is the total number of coordinates, right? And that's how many coordinates we would need to specify the total arrangement of the molecule, or the location of every atom, say, right? I've used up 6 of those so far, 3 for translation and 3 for rotation. So I want 3n minus 6 to be vibrations, okay? If the molecule were linear, then that would be 3n minus 5, because then I would have only 2 rotational modes that were available. Right? So in this case, that means that I should have 6 different vibrational modes. Okay. If I have to take a guess at how much those are going to contribute to the heat capacity, because vibrational modes usually are not significantly excited near room temperature, I'm still going to guess that this is roughly 0. Okay. Likewise, I'm going to say that my ammonia is not electronically excited at room temperature. Okay. So if I have to make just a back of the envelope kind of guess for what the heat capacity of ammonia should be at room temperature, I am going with 3R, I guess, based on that bit of thinking of things there. Okay. So let's take a look at the actual value and see how well our estimate does. Okay. Here are some data for how we would go about actually finding this if we wanted to do it for real, okay, before we cut to the answer of what the heat capacity really is. This says that this is my translational piece, this is my rotational piece, right? And then all the rest of that stuff is my vibrational piece, okay? In this case, in the diatomic case, we had just R for the rotation, and then we only had one term here instead of this summation, right? Because we only had one vibration. Here, I do in fact have 6 vibrational modes, and I went and I looked up, actually in your textbook, to be honest, in that table that I've been mentioning, I looked up the vibrational and rotational thetas for ammonia. Okay, these are the various vibrations in increasing, in order of increasing frequency or increasing theta there, right? Notice that even the smallest one is 1360 Kelvin. So if I'm at room temperature somewhere near 300 Kelvin, I'm at a significantly lower temperature than that, right? So my sort of 0th order guess that says the vibrations do not get excited is looking pretty good. Right, the rest of the vibrations, once I get past that first one, my approximation becomes even better because those temperature numbers are going up rapidly, and that means that the magnitude of these terms is going to be shrinking as I go up through those different vibrations. I also checked the rotational temperatures, although I didn't actually type them in the slide. I did note that all of them are below 14 Kelvin, right? So if my temperature again is near 300 Kelvin, then I'm well above that rotational temperature number for all of them. That means the available energy is much bigger than the spacing between my energy levels, and that means my high temperature limit approximation should be really good for that, right? So if I wanted to get a value for the heat capacity, I could in fact just use this equation, right? And all I'd have to do is pick a temperature, an exact temperature number, and then plug these 4 numbers in there with the appropriate degeneracies accounted for, and I would get a value. What I did instead of doing that is I looked up the heat capacity of ammonia at 298 Kelvin. Okay, that calculation is worked out in your textbook. It is, as it says here, example 5G. Okay, and it turns out that in terms of R, the heat capacity at 298 Kelvin is about 3.27 times R. Okay, which turns out to be this number there. Okay, and we could do that by doing the full calculation. We could alternatively look up an experimental value of that heat capacity pretty easily and compare those, and they match well. Okay. Of that, 3R was what I guessed would be the contribution from the translation and rotation, right? So the remaining about a quarter of R, or roughly, I guess, roughly 2 of those joules per Kelvin per mole is going to come from the vibrational part. okay? That's about 8% of the total heat capacity coming from vibration, right? If I flip back for a second to the slide that has those temperature numbers here, the vast majority of that vibrational contribution is going to come from this top vibration here, right? Because it's the one that's going to have the largest term, right? Because it's got the lowest vibrational temperature constant, so it is the most likely to be excited, right? And then there's a little bit from the second vibration, and then by the time I get to the two that are up with temperature constants near 5,000 Kelvin, I'm going to have decreasingly significant contributions from those, right? If instead of doing room temperature, if I raise the temperature, if I go up to 1200 Kelvin, right, then I'm now, flip back for a second, at 1200 Kelvin, this one in particular, my temperature, my actual temperature is now on the order of that first theta, right? So I'm beginning to have significant possibility of vibrational excitation there. When I do that, my heat capacity rises up and it goes to be over 6R now, right? So I've nearly doubled the heat capacity by raising the temperature up. All of that additional heat capacity is coming from vibrations now, right? So at the high temperature, I get most of the heat capacity, over 50%, is now coming from vibration, whereas at the low temperature, near room temperature, almost none of my heat capacity would be due to vibrational motion, right? So the fact, if you think back to the graph we looked at, which was for diatomic molecules, but we had the graph that it said that first I had a plateau that was for the translational part, right? And then I got rotations, and then I had another plateau that came in for vibrations, right? That same sort of general form will occur for our polyatomic molecules, except that out here, instead of having just one step there, we would actually have a series of steps that were kind of all getting commingled with one another, because I'm populating those different vibrational states at different rates because they have different frequencies or different theta constants associated with them. All right, that gets us a lot of connections between our partition functions and actual thermodynamic quantities, okay? The next stop on our tour of things is to imagine and work on taking these things we've put together now and work to try to put together a calculation that would get us an equilibrium constant for a chemical reaction, right? That calculation is pretty involved. So what you're going to find for that one is, again, going to be two videos, one in which I will lay out the actual arguments for how we would go about doing it, and then a second one in which I will spend an unduly long amount of time just doing the calculation for a relatively simple equilibrium, just to illustrate the fact that it's a fairly cumbersome process, but that it does work. Thanks.